This presentation is about the erosion mechanisms that operate in rain-impacted flows. For soil erosion to occur, soil particles must be first detached from the cohesive soil surface and then moved away from the site of detachment. Both raindrop impact and surface water flow can do this. This is a critical condition diagram. Basically, we have raindrop energy on the vertical axis and flow energy on the horizontal axis. In this case, we're using a thing called flow shear stress as a measure of that energy. Now basically this is about showing you that these drivers need to have specific energy values before they can cause detachment. Raindrop detachment only occurs when raindrop energy exceeds that energy that is needed to cause detachment. Once that occurs, you have raindrop-driven erosion. In this case, we have a slight change in the energy requirement when there is rain with no runoff, and this is because there are certain changes that occur in the soil surface that can change that energy requirement. In this case, we have a thing called crusting, which can make the energy more required. When water sits on the surface, it actually absorbs some of the energy that the rain drops have, and this then reduces the amount available for detachment, so you have to have a greater energy. Flow detachment only occurs when the flow shear stress is greater than that needed to cause detachment. And you can get flow-driven erosion when that occurs, and that means that both raindrop-driven detachment and flow-driven detachment can operate at the same time. When detachment occurs by raindrop impact, the particles can then be moved downstream by one or more transport mechanisms. The first two here are raindrop-induced saltation and raindrop-induced rolling. Raindrop-induced saltation occurs when the particles are lifted up into the flow, and because the flow is moving downstream, these particles then fall downstream as they return to the bed, and then they wait for subsequent impact before moving again. Particles that are stimulated to roll by raindrop impact again wait until they are stimulated again to move. When it comes to suspension in the flow, fine particles tend to remain in suspension always, and then they move with the flow without any further stimulation by raindrop impact, while the large particles then wait until further drop impacts will move them. The final two transport mechanisms are flow-driven saltation and flow-driven rolling. Now basically these occur without any raindrop impact to enable them, other than obviously by detachment, but once detachment occurs, these cause particles move without any further stimulation from raindrop impact. This is that critical condition diagram we saw earlier for detachment. Now, in addition to those critical conditions, there are critical conditions that are associated with the various transport mechanisms that we've been talking about. The first one for suspension is, of course, that there be water flowing and that the particles are fine enough to remain in suspension. When it comes to flow-driven transport of the coarse material, the flow needs to have a shear stress that is sufficient to enable flow-driven transport processes of rolling and saltation to occur. But below that critical shear stress, raindrop-driven transport can occur. There are a number of factors that influence what happens in rain-impacted flows. From the soil perspective, cohesion and interparticle friction influence detachment, and then once particles are detached, then their size and density are important. Raindrop size and drop velocities are important in influencing detachment and transport, as well as raindrop impact frequency, which is related to rainfall intensity. And then of course we have the flow effects, which are flow depth and flow velocity. This is equipment which enables us to control the conditions of flow over a soil surface in terms of flow depth and velocity. Using this equipment, it has been shown that raindrop-induced saltation discharges sediment in a linear relationship with rainfall intensity and flow velocity when flow depth is held constant. Here we're considering the situation where drop impacts cause particles to move limited distances from the point of drop impact, as happens in raindrop-induced saltation. So what that means is there's a zone at the bottom of the eroding surface where drop impacts cause particles to move across the downstream boundary, but ones from upslope do not, but they then contribute to the material that subsequently moved across the boundary. Basically there are many zones to consider because there are many different particle sizes and densities, and in this case the bottom zone we're looking at is 3 times longer than the top zone, and consequently there are 3 times as many drop impacts causing particles to move across the boundary in the bottom case than in the top case. And as a result of that, the discharge of material from the bottom case is 3 times faster than the top case. Now, as we noted earlier, raindrop-induced saltation is linearly related to rainfall intensity and flow velocity when flow depth is held constant. And we then has enabled us to develop this little equation which has a function in it which is an interaction between flow depth, which is the h, and d, which is the drop size. The drop size flow depth function in this equation accounts for 2 things. Firstly, it accounts for the ability of drop impacts to move loose material and cause detachment, and that decreases with flow depth as more of the energy is dissipated in the flow. Also, it accounts for the effect of how high the particles are lifted by each drop impact. Again, that depends on the energy that is dissipated in the flow, and also how the surface constrains how far the particles can be lifted. So we have basically 3 conditions to think about here. This one here is when the particles can be lifted up freely and the water depth doesn't have really any effect on how far they lifted and how far they travel. But if we have deeper flows, then the energy is less, and so the particles don't travel as far. And again, if the flow depth is shallower, then the water constrains how high the particles can be lifted. In the process, we get at fairly shallow flows, we get this function is small and increases until you get to a certain value, which is drop size dependent, and then it decreases as the flow depth influences the energy more. The particles that fall back onto the bed actually generate a layer of loose particles sitting on top of a cohesive soil surface. And that requires energy to move them, and this has caused that value Kp, which is the soil related factor, to vary with time. Now it actually varies between two particular states. One is when there's no loose material sitting on the surface and the drops are just detaching material from the underlying surface. And then the other extreme is when that layer of material on the surface completely protects the underlying surface, and it only then lifts up material that's been previously detached. And so we have a little equation here that enables us to go between those two extremes, and we have a thing called H, which is the degree of protection provided by those loose particles. There are many experiments reported in the literature where raindrop induced saltation controls the discharge of coarse material, and this equation could be applied. However, on sloping surfaces, flow depths and velocities are not controlled and are not known. Similarly, values of kpm and kpl and h are unknown, and generally there's lack of data of the size and densities of material that is being discharged. The complexity of the interactions between raindrop impact and surface water flow therefore generates difficulties in determining why different soils produce different erosion responses in many rainfall erosion experiments.